Welcome back. This is the last and final video on the effect of substituents. Now, if you notice, we have progressed forward slowly. We started off with the electrophilic substitution of just a plain benzene ring, right? Then we looked at the effect of just one substituent, whether it's ortho, para, or meta director. Now we're looking at a situation where we have two substituents, and one of them would control where the incoming substituent would go. Now you could ask, what if both substituents are the same? No, I did not do that option because that makes process easier. We're only looking at competition between two different substituents on the ring. Okay. Generally, out of the two substituents, whichever one is more activating generally wins the race. Now, if you look at this chart, previously I did not focus on it because that was not the focus at that point. Let's say we have two activating groups, like in case of amino and hydroxy. Then, as I said, the arrow goes up. That means amino is more activating, that is more reactive than hydroxy. Just let's say you have two deactivating groups, F and Cl, then F is more active, more reactive of the two, so Cl would be even more deactivating compared to an F. Okay, so the direction of the arrow indicates which one will be better of the two. Okay, but if the groups are activating and deactivating, then life is easier. Just whichever one is activating wins the race. Okay, so with that in mind, let's look at these two examples. The first one, well, right away we know that if this is the combination of reagents, we are going to be adding SO3H to the ring. Now, where does this go on the ring is a mystery. NO2 is deactivating and OH is activating, so OH wins the race. And OH is an ortho-para director, so with respect to OH, the position of it, this is ortho, this is an ortho, and this is a para position, right? Now, right away, I can tell you one of the product is really, really least favorable, and that would be this. Why? Because the incoming substituent is already a bulky group, and it has to go between two bulkier groups, makes this position a little overcrowded, so this is least favorable. That means let's go ahead and draw only the other two products, and out of those two, generally para position products are much more favorable, much more of a stable product compared to an ortho product. So this is, so it can go here, or it can go to the para position. One of them would be minor product, one of them would be major product. Typically, products that are para-oriented or major, typically ortho-oriented products are minor, so that means you could have, this would be the major, and this would be the minor. Okay, just like in the next case, this is a Friedel-Crafts acylation reagents, so that means right away we know when we combine this, we are going to generate an electrophile CH3CO+, and this is what gets added to the ring. Now, as with the previous case, NH2 is activating, NO2 is deactivating, so NH2 wins the race. And NH2 is also an ortho-para director. So with respect to the position of NH2, this is ortho, this is meta, which we don't care, and this is para. And as with the previous case, this particular product would be least favorable because of steric hindrance, which means these are the only two products possible. So that means we will go ahead and write this out. And as with the previous case, generally para products are much more stable versus an ortho product. So that's the ortho product. And let's go ahead and complete the para product as well. And there it is. This will be the major product because that's the para, and ortho product will be the minor product. All right, using the chart and all of the knowledge you've gained so far, practice these two problems and include your answers in the My Thoughts assignment. And that concludes the effect of substituents in an aromatic substitution reaction. Stay tuned for a brand new topic.